My name is Equivalence and I'll be chairing this session. We have three presentations, one from research track, one from resources, and one from journal track. And our first presenter is Luigi Asprino, and he'll present observing linked open data using equivalence set graphs. It is mostly flat and sparsely linked. Luigi.
Hello everybody. I'm Luigi Asprino, and I'm going to present an empirical study on the overall semantic structure of linked open data. The collection of linked open data datasets forms the largest knowledge graph that is available today, and it gives us the opportunity to study how knowledge behaves at very large scale. In this work, we are interested in studying how classes and properties are used in practice. In empirical studies, the first problem that you have to face is to choose an empirical basis for your analysis. So we chose Load-a-Lot as an empirical basis for our studies, which contains 28 billion triples crawled by Load Laundromat. And over this data set, we are interested in answering the following questions. How much classes and properties are interlinked? And what is the shape of ontological hierarchies of classes and properties? And how classes and properties are actually instantiated? Similar work has been done since the early stage of the semantic web, but sometimes with different perspectives. Some of them assess the use of specific properties like same as, the use of blank nodes, the coherence of large dataset, but sometimes on a smaller scale than ours or on a single dataset. In order to conduct our analysis on such a large dataset, we introduce a novel data structure that we called equivalence set graph. The idea of an equivalence set graph is to provide a compact view of very large RDF graph, which focuses on specific dimension that we want to observe. Over this data structure, we have defined some metrics to conduct our analysis, and we devised an efficient algorithm which is polynomial in the number of triples analyzed, to build such graph from large RDF datasets. And we perform, with such framework, we perform an analysis to study how classes and properties are actually used in linked open data. So what is an equivalence set graph? Here is an example where there is a property, dbpedia author, which is equivalent to schema author and Wikidata P50, and dbpedia author is also subproperty of Dolce co-participates with. And the idea of the equivalence set graph is that is to collapse equivalent nodes in a single nodes while preserving the specialization relation among these nodes. So from the input graph, there will be a node containing schema author, P50, and dbpedia author, which specializes a node containing only Dolce co-participates with. And in doing this, the only thing that you have to ensure is that the equivalence relation that you choose to form this equivalence set graph is reflexive, symmetric, and transitive, and the specialization relation that you choose to create edges is reflexive, antisymmetric, and transitive. So we computed the equivalence set graph for properties in Load-a-Lot, which contains 1.3 million properties organized in 1.3 million equivalence sets. So as you can see, equivalence is not so much used among the properties, and it contains also 147,000 edges. So also specialization is not much used. And in doing this, of course, we took care of possible equivalence or specialization of standard properties, like in this example, where there is a property from Wikidata, which is P1647, which is equivalent or subproperty of subproperty, and this property is used to say that DBpedia author is subproperty of Dolce participate with, and you, of course, don't want that your resulting equivalence set graph is different from the previous one. And we observed that the equivalence of specialization of standard properties is something that really happens in linked open data, since we observed that there are 447 specialization, let's say, of subproperty of, and 379 specializations or equivalents of subclass of. And by changing the notion of equivalence, you can compute an equivalence set graph for classes or individuals. And here is an example of an equivalence set graph for classes, where we used as an equivalence notion owl equivalent class. So the input RDF graph, in the input RDF graph, there is class DBpedia person, which is equivalent to fourth person and Dolce person, and these three classes form an equivalent set, which specializes an equivalent set formed by org agent and Dolce agent, and there is another equivalent set which contains only social agent. So we computed the equivalent set graph for classes in Lodelot, which contains 4.8 million classes organized in 4 million equivalent sets. So as you can see, equivalence is a bit more used for classes than for properties, and this graph contains 5 million edges. Also specialization, it seems that specialization is a bit more used among classes. Computing an equivalent set graph is actually really simple. The algorithm simply goes through equivalence triples like DBpedia author, equivalence property, schema author, and in this case the subject and the object, DBpedia author, schema author, are not contained in any equivalent set, so a new equivalent set is created. Same for Wikidata P150, equivalent to GND author. And here, DBpedia author, equivalent author, and BibTeX author. Here, BibTeX author is not contained in any equivalent set, but DBpedia author has an equivalent set yet, so we add BibTeX as author to the equivalent set of DBO author. And of course, you have also the case when when subject and object are contained in two different equivalent sets. So, like here, DBpedia author, equivalent property, GND author, and you have to merge the two equivalent sets. When the algorithm has done with equivalence triples, goes through specialization triples like DBpedia author, subproperty of Dolce co-participates with, and simply adds an edge from the equivalent set of the subject to the equivalent set of the object, and in this case also add a new equivalent set, since Dolce co-participates with is not contained in any equivalent set. It turned out that the time complexity of the algorithm is quadratic in the number of equivalence triples and linear in the number of specialization triples. And the space complexity of the algorithm is quadratic in the number of entities inside the graph, like the number of properties, the number of classes, or whatever you want to observe. And the time for computing needed for computing the equivalent set graph that I showed is on this machine is 4 hours for the equivalent set graph for properties, and 14 hours for the equivalent set graph for classes. And this framework is available online on GitHub, and is based on some popular libraries. So we have defined some metrics on this data structure. And we counted the number of isolated equivalence set that are nodes in the graph without any outgoing or ingoing edges. And it turned out that the the graph for properties contains 88% of isolated nodes. This means that the graph is very, very sparse. And we also counted the number of top-level equivalence sets, which are nodes without outgoing edges. And also we observed that 90% of nodes in the graph for properties are actually in the top level. So this means that the hierarchy of properties is very, very flat, while the top level of classes contains 1/3 of the nodes. We also computed the weakly connected components of the graph, which are a weakly connected component is a subgraph of the graph where you can go from one node to another without considering the direction of the edges. And it turned out that the graph for properties contains 1.17 million different connected components, and that for classes contain 449,000 weakly connected components. And we also observed the size of the component. That means the number of nodes in a component. And we saw that there are many components with a really small size. So this means that the hierarchy of classes and properties is formed by a lot of small trees, disconnected small trees. And we also observed the height of the nodes, which is the height of a node is the size of the path from a node to a leaf node. And we observed that almost all the properties have size 0, and almost all the classes have size 0, 1, or 2. So here is like what the property hierarchy looks like, and here is something like the hierarchy for classes. So we also assessed the extensional size of the entities in the graph, which is for properties the number of triples with that property, and for classes the number of individuals of that class. And from the size of the entities, we computed the direct size of the equivalent set, which is the sum of the sizes of the entities inside the set, and the indirect size, which is the direct size of the set plus the direct size of the nodes in its transitive closure. And turned out that properties and classes have two different behavior. Properties are mostly instantiated, and the classes are mostly uninstantiated. So, conclusions and some speculation on these observations. So, we observed that equivalence and specialization are sparsely used in LOD. So, we can only speculate on what this means. Probably, we don't know if there are duplicates in these hierarchies, or if is it difficult to align properties, or simply people do not want to align their properties to other properties, or classes, or whatever. And you also observed that hierarchies are actually mostly flat. We saw a little bit more structure in the hierarchies of classes. So we can, let's say, speculate that ontology engineers probably put more care into class hierarchies than property hierarchies, or that probably the hierarchy of properties makes more difficult to create an hierarchy of property instead of creating an hierarchy for classes. And we also observed two different behavior for classes and properties in the instantiation. Now the question is why this happens. Probably we know that in some domains it is normal to have uninstantiated classes like in biomedical domain, but we don't know if this reason cover all the uninstantiated classes, so it is something that we have to assess in the future. And we have to assess if the knowledge domain influence this design choice. So future work, we plan to try to empirically prove or confute these speculations and to assess the possible influence of knowledge domain in what we observed. And we want also to extend the framework so to try to analyze the use of other kinds of relations that are commonly used in knowledge engineering, like this joint nest. Okay, thank you.
Thanks, Luigi. Any questions? Okay, I have a question.
Yeah.
You mentioned that in your future work you are going to take a look at how domain actually influences the statistics. Do you have any plans on how do you actually determine the domain of a triple or a property?
Okay. We have a metadata from the load cloud net, so we can actually first use that metadata. And but the classification of the dataset of load cloud net is not so rich in terms of expressivity. You have only 8 classes for classify your dataset. So actually we are trying to let's say classify the dataset by using the natural language that is used in a dataset. So for each dataset we plan to create like a virtual document, and then try to make a classification of the domain of that document. So we are going in that way. Okay.
Okay, thanks. Any other questions? Okay, so maybe one more from me. When you started with this experiment, did you have any expectations? Did you have any idea how it may look like in the end?
Actually not, and the results was quite surprising for me because actually I didn't expect to see so much classes, empty classes, but it is reasonable to think that there are some empty classes, because we know that in some domain it is reasonable to have some empty classes, like in biomedical domain, but no expectation.
Okay, thank you. Any questions whatsoever? If not, then let's thank our speaker again. And now our second presentation by Aiden Hogan, BTC 2019, the 2019 Billion Triple Challenge Dataset. It's a resources track presentation.
Hello. So to briefly mention before I start the talk, I've been living 6 years in Chile, and you've probably seen that there's been some incidences in Chile recently. It's kind of difficult for me to be here because we've been in the center of a lot of protests, a lot of attention. So this was me 2 days before leaving for the conference. This was the day of leaving for the conference. So it's quite a dramatic situation there. The international news has focused mostly on violence, on protests, and so forth. But just to mention that it's important to keep in mind that most of the protests have been peaceful and people are just asking for reform and change. Okay. So I'm going to present a data set. In fact, my presentation is quite simple. What we have done is crawled a new version of the BTC datasets. Does anyone know, has anyone seen or used the BTC datasets here before? Nobody? My presentation is flickering. Nobody here has used the BTC dataset? Do you remember the BTC challenge? You know what it is. Okay, so the BTC, the Billion Triple Challenge, started in 2008. It was proposed by Jim Handler and Peter Mika. The idea was that there was a lot of criticism at the time, in those years, of the semantic web community and the semantic web technologies in general. People were saying essentially that they didn't scale, they weren't realistic when faced with real-world web data, for example. So the idea was to crawl a bunch of data and then see what people could do with it, see what the creativity of the community could come up with, right? So this was 2008, focus on scalability and real-world data. Yeah? So this challenge continued on and off down through the years in ISWC. So from 2009 on, Andreas Harth was a central figure, also supported by Tobias Kaufer, who's here. So we had data sets from 2008, 2009, 2010, 2011, 2012, nothing in 2013, 2014 again, and then nothing in 2015, 2016, 2017, 2018. Okay? So, is this a problem? Looking at the literature, in fact, these data sets have been used by a wide variety of communities for a wide variety of topics. This is a survey of the papers that have used BTC data sets for their evaluation. Okay? So we see lots of colors. What are the colors? The colors reflect the topics. Okay? So we see querying, reasoning, search, linking, visualization, and so forth. So we see a lot of topics. Another thing that's quite interesting is the communities. So we see Sigmod, databases, SEMsearch, we see SICM, we see KDD, ECIR, and so forth. We see logic communities, we see database communities, we see information retrieval communities, and so forth. What else is interesting here? The scale of the data. So essentially these communities are using these data sets as a highly diverse graph, yeah? A very large scale graph on which to do experiments. So we see a wide diversity of approaches using the BTC datasets. I have a food theme in this talk. I'm not sure why. I thought the talk was before lunch, but you've all eaten, so maybe not so interesting. So a second type of approach or a second type of use case for these datasets has been to understand web data. What are people doing on the web? What sorts of vocabularies are they using? How are they defining the semantics of these terms? Here we see some works on linking. How are things linked? Studying how data on the web is linked. We see work on studying ontologies or vocabularies, how these are defined, what sorts of features of OWL are most commonly used. We see some study on temporal aspects. And we see some examples. It was also used to see how data are published. This was specifically to do with Sparkle endpoints. So it's also used not just for benchmarking, for scale, for efficiency, and so forth, for real-world data sets, but also to understand what is going on the web. Yeah? Okay, not so diverse, but also some different approaches. So we haven't had a data set since 2014. Could we use another data set, right? So what other data sets could we consider? There's the Web Data Commons that's often extracted. This is extracted from the Common Crawl. What is the Common Crawl? A huge crawl of web documents, yes, of HTML documents. So what's the problem with this? Could we use this? Well, it's great for embedded data, this sort of RDFA, schema.org, OGP. Yeah? It's not great as a graph. It's not really a graph as such, right? You can't really do random walks. You can't really do centrality on this because the nodes don't really connect. The data are so shallow that, okay, everything points to maybe the classes in OGP or in schema.org, but the instances are not really linked. Okay? I put con here in inverted commas. It depends on what you want to do. Right? I don't want to say this is a bad thing about the data set. It's just an aspect of the data set that's maybe not ideal for certain cases. We also have, for example, Log Laundromat, where we have people can submit data sets and they get cleaned and so forth and curated. This is great for working with selected data sets. Yeah, you can also take multiple data sets and you can work with those data sets together. What's the con? The con, again, in inverted commas, yeah, because it depends on what you want to do. The con is that it's not really open web data. Yeah? So there's some sense in which it's maybe selected data sets and so forth. So neither of these really meets what we have used, what the use cases have been for the Billion Triple Challenge data set. So we kicked Andreas away. I can say that because I'm a good friend of Andreas. So I proposed to a PhD student to crawl a large data set. Yeah, so we proposed to create BTC 2019. In fact, that's not the real story. The real story was that we wanted to do an analysis of the use of literals in web data, and we needed to do a crawl anyways. So we did the crawl, we had the data set, and we figured maybe other people would use this. So that's why we submitted this resource track paper. And we contacted Tobias because he has expertise on the crawling aspect and how things were. He was the one who did the 2014 crawl. Yep. So what did we do? We crawled RDF data for 1 month. We crawled RDF XML, Turtle, and N triples. Yeah? This is the first time in 5 years this had been done like this. How did it go? Here we see the days. We see from 0 to 30 days, 1 month. And here we see the progression of how many quads, how many statements, how many triples we had crawled every day. Right, so we store the triple, and we store a fourth element, which is the document from which that triple was taken. Yeah? So what can we clearly see here? We can see a slowdown, right? So why do we have this slowdown? Why does this occur? So what happens is we have something called the notion of a PLD. What is a PLD? It's a website. Yeah? So dbpedia.org, bbc.co.uk. Yeah? And what we see is that as the crawl progresses, here, we find more and more PLDs. But after some time, this point here, we don't find any more. We don't find any new websites hosting RDF data. Yeah? After a couple of hours, or after a couple of days, sorry. So what do we see here? We see the ones that are actually active, where we haven't crawled all of the documents in that website that we know of. Yeah? So when we get to this point here, we have maybe 10, 15 active websites that we can access, and we can only access every website once every few seconds. Yeah? We can't crawl lots and lots of pages from the same website within a second. So essentially, this becomes the limit of performance. Yeah? So we can only crawl maybe a page from every website once every 5 seconds to avoid a DOS, a denial of service attack, and this makes the crawl slow down. What's the data set we achieved after 1 month? So after why 1 month? Essentially, if we continued, you could see that the data set is not going to grow very much, and it's certainly not going to get much more diverse. Yeah? Or very unlikely to, unless we hit some link that opens up this new part of the web we haven't seen, which seems extremely unlikely, right? So what was the data set we had after 1 month? We have 394 websites, effectively. dbpedia.org, for example. linkdata.org, and so forth, data.gov. We'll see some examples later. 2.6 million documents, 2.2 billion quads, 256 million triples, 38,000 predicates, 120,000 classes, by which I mean instances, values of RDF type, okay, and 1,700 namespaces. Anything unusual about this table? Sorry? Yes, exactly. Yes. So we see we have many, many more quads than triples. So what does this mean? This means we have a high duplication of triples across different documents. On average, each triple appears in about 9 documents, right? Does that make sense? Why did this happen? We were surprised by this. We hadn't seen this before. This wasn't something that usually happens in BTC. We'll come to that. First of all, where does the data set come from? Yeah, so we have all this data here. It looks pretty delicious, but what's the source of this data? Yeah, where did it come from? So we have ways of analyzing this, various ways. So the first we're going to look at are the documents we have per website, right? So if we look at the documents per website, here we have the top 10, and this gray thing here is the rest. Yeah? So we see more or less a balance between the top websites, DBpedia, some usual suspects, lock.gov, bnf.fr, and so forth. Yeah? Here we see Wikidata, linkdata.es, and so forth. Yeah? If we look at it a different way and look at it in terms of triples per PLD, we see that there's a pretty big chunk of the data, almost, or over half, I guess, comes from wikidata.org. Yeah? And then we have DBpedia, and then we have various others that we saw previously. So that's a little bit unusual. So Wikidata here is number 6. Here it's number 1. And if we look at quads per PLD, we see that 92%, I think, of the quads come from Wikidata. Yeah? So how do we explain this factor? So we have Wikidata is number 6 here, and it's 91% of the quads. Yeah? So what happened? So what happened is that the Wikidata linked data documents are massive. Yeah? So they include labels, various labels for different places in various languages. Not only that, it contains all of the labels for all of the properties and all of the classes, the neighborhood, the entire neighborhood of the entity. So there's on average tens of thousands of triples in Wikidata. Yeah? Also repeated, because we have the properties and the class information within every entity. Yeah? So therefore we have a huge duplication of the data in terms of quads for Wikidata. Okay. So what about vocabularies? What vocabularies are we seeing here? We see the usual suspects, RDF, RDFS, FOF. So what are we counting here? Sorry, the max here is the number 396, was it? 394? The websites, yeah? So we don't want to count documents. We obviously don't want to count quads because that's extremely biased, yeah? How many websites are using these things? So we have RDF, RDFS, FOF, OWL, DC elements, DC terms, SCOS, geonames, or geo vocabulary, admin, I don't know what that is, and schema.org. Yeah. What about properties? RDF type, FOF name, label, so forth. FOF primary topic, OWL SEMAS, FOF knows, FOF maker, DC elements title. And classes, person, personal profile document, class, ontology, object property, and so forth. Okay. So what is interesting to look at is the differences between this data set and the one 5 years ago. Maybe we could learn something about what happened in between, because we use pretty much the same methodology actually as 2012. There was something slightly different in 2014 in that it included RDF-A data, and it ended up having hundreds of, no, not hundreds of millions, tens of millions of documents that had like 2 triples. So we just decided to get rid of that. Yeah? So it's maybe more interesting to compare with 2012. Highlighted in red, all of the numbers that are lower. Yeah? Highlighted in orange, it's lower than 2014. Yeah? So we see less data. We've collected less data this time. Can we explain that? Kind of. If we look at the top websites producing data in 2012 and 2014, we see all these red websites. What are these red websites? Things that no longer publish data. Yep. There's no longer Freebase. We no longer find data.gov.uk, which I don't know why. So I don't want to say this is super important. I don't want to say these data sets are offline. They no longer appear in our crawl. Yeah? So there might be several reasons for that. Freebase is definitely offline. Kasabi is definitely offline. Opera is definitely offline. Some of them I don't know. So we see that there's some large volume websites have gone offline. Why might this be? It might be maybe a trend towards maybe linked data is not such a tempting prospect to publish linked data. Maybe there's not so much emphasis on this anymore. In terms of the new data sets, we have wikidata.org. Yeah, so we lose a lot of data sets and we win one. Yeah. Again, I don't want to imply that all of these are offline, but they don't appear in the crawl that uses the same methodology as we had in 2012. So there's something strange going on. We looked into it and mostly they were offline or there was errors. They were no longer serving the data correctly. The data are online. You can download the BTC 2019 dataset on Zenodo. It already has 3,990 downloads, which is a nice big number. Slightly lower number is the unique downloads. So we have 300 unique downloads, which we're pretty happy with. Yeah, and we've served about 1 terabyte of data. So yeah. So what's the goal? The goal, again, is that these papers that were previously using the BTC datasets, they can continue to use some more modern, up-to-date, fresh data. Conclusions. We see that the Billion Triple Challenge datasets have been widely used in the literature by various communities for various purposes. In terms of the new dataset, we have some details. We see here it's the first one in 5 years. We crawl these RDF formats, this number of documents, this number of domains, and so forth. Yes, and it already has about 4,000 downloads, 300 of which are unique. Open questions: do we continue with these data sets? Is it useful to continue using these data sets or not? Maybe there's other types of data sets would be more useful to have. Do we include, for example, RDFA? Do we include JSON-LD? What about microdata? Our decision was not to include these things at the moment. Maybe JSON-LD there's a better argument for. And also, what happened to all these data sets that we saw back here? Yeah, what's going on here? This is super interesting to look at and see what's happening. With that, yes, BTC 2019, taste the rainbow. Thank you.
Thanks for the presentation. Are there any questions?
Thanks, Aidan. Very useful. Actually, I have some curiosity. So, where are all the data sets from biomedicine, for example? They have from biomedicine, biodata sets.
Biodiversity?
No, even biomedicine, genetic data sets, or molecular biology data sets.
Why don't they appear
They
here?
used to be a large part of the cloud.
The cloud is very different.
I know, but...
The cloud, yeah. So why isn't there anything? There used to be, for example, you see on the left, there was linked clinical trials at some point. That's gone offline. Mm-hmm. There was Bio2RDF. Bio2RDF should, in theory, appear here, but it apparently doesn't for whatever reason. Mm-hmm. Other data sets, I think also, if you talk about the ontologies, for example, the more like biomedical ontology data sets, they're probably too small in terms of total volume to appear in the top 10 that we have here, right? So they could be further down. I think BioPortal does appear, but lower down, like number 60 or 70. There is a couple of other biomedical data sets, but they're not very large, I understand, in their A-box or in the linked data that they're publishing, compared to Wikidata and DBpedia. Although I'm not sure. You look like you disagree.
Yeah, I guess the point. By the way, why don't you simply include all the possible formats? The RDF is an abstract data structure, so any serialization should work. No?
This is a long and storied debate. When we were working in Derry, there was two search engines. There was something called Syndice, and there was something called Swizzy. And I was working with Andreas and Tobias on this. And we would crawl RDF XML, whereas Syndice would crawl RDFA, microdata, microformats, and they would claim they had 1 billion documents, yes? But each document only had 2 triples, and it didn't form a graph. So we focused on sort of higher quality data. Essentially, here in 2014, they included the other formats. They included all the formats. And I've worked with the data, and other people have worked with the data, and the first thing you generally do is just throw all that away. Yeah, because it's not useful for doing basic graph pattern evaluation. It's not useful for studying. It's just, this is the title of this web page, and this is the links it has, right? So it's generally very shallow, the data that you get from RDFA in our experience. Now, if that improves or changes, and there's also another data set that provides that sort of data, which is the Common Crawls data set. And it's super interesting to work with this data, but it's somehow, that's not really the goal of, it doesn't fit with a lot of the use cases for BTC. But it's a valid point, yeah. I don't know. Maybe it's good to include these formats.
Any other questions?
Maybe a stupid one, but why do you exclude Sparkle endpoints?
I like stupid questions. We don't, in a way, because a lot of these data sets here are linked data wrappers that actually call a Sparkle query in the back end. So this could be a different interface to the same data, you know what I mean? Otherwise, yeah, I mean, that's probably the best way to summarize that, yeah.
Just a very quick question. If you have to compare this to what we used to see in the cloud picture, because my understanding is that what comes out from here is that now it's smaller, right? So do you think this is a good representation of what linked open data is today and how big it is with respect to what we used to use?
Yes, it's a very good question. So I've spoken with people about this. The old log cloud was based on metadata that people had added themselves manually, right? And we never really saw the data that was claimed in that old log cloud. So there was a big gap, right? The old log cloud, we would take one example IRI or one example link from all of them and try to crawl, and half the data sets would never appear. Yeah? The new log cloud is based on a crawl. Yeah? So it's based on something similar to what's done here. But what they do is they define the notion of a data set in a different way, which is maybe fair, I'm not sure. How it works is we would define here dbpedia.org as one website, one domain. They would say, for example, es.dbpedia.org, for.dbpedia.org. These are different bubbles. Now, I don't know the exact criteria used for this, but it looks like there's a lot of bubbles, but if you look at it, many of those bubbles sometimes come from the same publisher, the same group, the same domain. Yeah, so there's a question of maybe not wanting to shrink the log cloud, for example. There's a question of trying to, Number of triples is very difficult to estimate, but I mean, the classic example against that was linked open numbers by Denny and Marcus, where they took any natural number, like 5, they would say what the next natural number was. So they published this. You could actually continue crawling infinitely all the natural numbers, so there is essentially a potentially unbounded number of triples. In general, the number of triples, I mean, there are very large data sets for sure. Yeah, and there are some data sets that are pretty much exactly what they claim to be. Others are not accessible for maybe technical reasons, or maybe the data have gone offline. But yeah. So it's very hard to say. Yeah.
Okay, let's thank the speaker again.
Thank you.
And the third presentation will be by Evangelos Kalampokis on modeling linked open statistical data, a journal track submission.
Okay, hello. My name is Evangelos Kalampokis. I come from Greece. I am affiliated with the University of Macedonia in Thessaloniki in Greece, and also the CERTH, the Center for Research and Technology in Thessaloniki, Greece. Okay, my presentation comes from the journal track, and the paper that I'm going to present is on modeling linked open statistical data. Okay, the outline of my presentation is really typical. We will start with the motivation. I'm going to briefly present the objective of the paper, the approach that we followed, the results of our work, and I will conclude with some future work suggestions. Okay, so let's see the motivation part. And what we are studying is open statistical data. We know that a major part of data concerns statistics such as demographic, economic, and social indicators. We refer to this aggregated data as open statistical data. And I need to say that we do not only here refer to data that comes from national statistical institutes. Open statistical data can also produce public administration authorities that can aggregate some transactional, some operational data. They want to anonymize some operational data, so they aggregate them and they provide them as open statistical data. A typical, a common structure of all these open statistical data is that can be conceptualized as data cubes. Okay, so all these data are describe a measure, for example, let's say the unemployment rate, and to do so they use some dimensions. For example, we can say that the unemployment rate in Greece in 2001 for the age group of people from 25 until to 49 years old was 10%. So we need to describe measure based on some dimensions. This is the typical data cube structure that we can find in data warehouses. Okay, so we have open data, we have a specific type of open data, and the question here is if we can publish this open data using linked data technologies, then we can integrate all this data on the web, and then can we perform some very interesting analysis by combining different data sets across the web. So we refer to all, by applying linked data technologies in open statistical data, we use the term linked open statistical data. And we know that we have developed a number of standards and vocabularies in order to be able to facilitate this creation of linked open statistical data. The most typical vocabulary is the RDF data cube vocabulary, but we have some other supporting vocabularies such as COS and XCOS. And of course, we have also some control vocabularies or code lists that can help us in order to be able to create linked open statistical data. So we have a control vocabulary regarding the units, and for some other widely used concepts that have produced by the transformation of X standard. So based on these vocabularies and based on these standards, we have created a number of official portals that provide linked open statistical data have been created. So we have some public authorities and governments have created such portals, for example, the Environmental Department of the Flemish government, the Ministry of Housing, Communities and Local Government in the UK, the Scottish government, the Japanese government have created dedicated sites for providing linked open statistical data. But also we have some national statistical institutes that provide such type of data. For example, the ISTAT, the Italian National Institute of Statistics, and also the Irish CSO provide linked open statistical data. So far, so good. So what is the problem? The problem is that although we have some web standards and we have agreed on some vocabularies, the people that try to produce and create linked open statistical data need to make some important modeling decisions by themselves, and they do so in an ad hoc manner, and this way we result in data sets and in portals that are really difficult to combine. We can create data silos, and these data are really difficult to be able to analyze together. And another issue is that we can create software tools in order to analyze this type of data, for example, to some simple visualizations. But the problem is that these tools cannot be reused across different data sets. So we started with my team a few years ago to develop some tools in order to be able to easily exploit this type of data. So let's say to create a tool in order to be able to create some visualizations. And the problem was that the tools that we created could only be used by specific data sets and for specific portals. So the objective of our study was to identify all the modeling questions that a linked open statistical data publisher has to answer in order to be able to create linked open statistical data. So what are the different decisions that one should be make in order to be able to create this data? And we refer to this question as modeling challenges related to the creation of linked open statistical data. We also wanted to provide answers to these questions. Okay, we have identified the questions that someone need to answer, but we also need to provide to them, to people, ready to use answers. So we refer to these answers as modeling approaches or modeling practices that can be followed. So in order to do so, we employed, let's say, a scientific method. It's called the Delphi method. And we selected this method because it involves experts in a domain. So we wanted to see how people and why people make specific decisions on the way that they publish their data. So we wanted to go back to the experts to see what problems they faced, what were the challenges, And also, we wanted to see what was the reasoning behind these challenges and the approaches that they followed in order to address the challenges. So here we have a facilitator. We were the facilitators, and we collected created a group of experts, and by having some rounds of questionnaires, we wanted to achieve consensus on some issues, and the issues was the modeling challenges and the modeling approaches. So some characteristics of the Delphi methods is that the experts reassess the initial judgments and they come back in order to provide their feedback. The participants remain anonymous to each other even after the completion of the final report. And also we can have, as I said, multiple iterations, but typically 2 or 3 iterations are enough. So in our approach, we involved the experts, 9 experts that were involved in the creation of official linked open statistical portals. For example, in the Scottish, in the UK government, in the Flemish government, in the European Commission's digital agenda, in ISTAT, etc., etc. And also some people that were experts, for example, one of the creators of the QB vocabulary. And we had 2 rounds of Delphi rounds. In the beginning, we started with a preparatory phase. We created the first questionnaire based on some initial analysis of the portals, of the vocabularies, identified some challenges and some practices that can be followed. Based on this initial preparation, we created the first questionnaire. We delivered the questionnaire to the experts. Okay, the experts have identified some areas of disagreement and agreement. We identified the pros and cons of some practices and some more challenges and practices that we needed to study. Based on the results of the Delphi first round, we created a second questionnaire and we delivered this questionnaire back to the experts. And after the second round, we concluded to the modeling challenges, to some agreed or let's say best practices, and some analysis of practices in challenges where consensus was not achieved. That was our approach. The results, as you can see here, we have identified a very big number of challenges, and all these challenges are related to the different structure of the cube model. For example, how can we define a unit? How can we define the measures? If we have multiple units per measure, if we have multiple measures per cube, how can we define the dimensions, etc., etc. So here we have a long list of challenges and specific questions that people should answer in order to be able to publish their data. I'm going to give you very briefly some examples of practices that we have came up in order to address these challenges. For example, let's say for the units of the measure, we have concluded that there was an agreement, had achieved consensus that a unit of measure should always be included, and we should use the SDMX attribute unit measure. Also, we need to reuse URIs from the QE UDT code list. And also, the unit should be defined at the QB observation, but also to the QB dataset in order to facilitate indexing. Okay, we have many approaches that can be described. For example, for multiple measures, the QB vocabulary proposed different practices. So we identified the advantages and disadvantages of each practice, and again we had a consensus on which of these practices we should follow. The values of the dimension, again here, how should we define these values of dimensions? That we should always define the range, and even if we have code lists, again, we should also define the range of the dimension using the SCOS concept class. Okay, and regarding the single value dimension, this is too much detail, I don't have much time. Again, the thing is that we have identified 19 approaches for modeling linked open statistical data. All the definitions, along with really detailed descriptions and the working example, can be found in our journal paper in the Journal of Web Semantics. Future work. The thing is that we have identified 19 approaches, And in order to address some challenges, the thing is, many of the challenges are still open. We have open challenges, and again, we have a list of these challenges. For example, I can say that the code list for measures that could be reused by LOSD publishers, we don't have code lists for the measures. And for sure, the method that is used to calculate a measure should be also specifically, explicitly defined. So, for example, unemployment. How do we measure unemployment? What do we mean by unemployment? Different countries can refer to unemployment, different methods to calculate, to have different methods for calculating unemployment. And more things, we have more open challenges. It is indicative that in a recent work that we have also conducted, we have identified 20 interoperability conflicts in linked open statistical data portals by using some frameworks from the literature regarding interoperability conflicts. And we studied all the portals that have published linked open statistical data, and we have concluded that we have identified 20 such conflicts. The thing is that if we use the approaches and the practices of the paper that I just presented, we could have solved 11 of these 12 interoperability conflicts. But again, many of them still remain. For example, we have 9 conflicts that need to be resolved. So, very quickly, that's our work that we have performed. Thank you very much, and if you have any questions, I can answer. Thank you very much.
Thank you. Are there any questions?
So the cube model kind of assumes 3 dimensions, but I was wondering, if you have more features to consider with the central tendency and dispersion measures, for example, if you have a table with multiple columns describing certain, statistics, how would you actually describe that? Would you have to translate that to a cube model first to use your work?
The cube vocabulary? So what do you mean? You can describe as many dimensions as you want. So not only 3 dimensions. So so because at the beginning I presented a picture with a cube. Okay. Right. Yeah, no, this is just for simplicity reasons, just to present it, because we can visualize a 3-dimensional cube. But no, the RDF data cube vocabulary can express many dimensions, n dimensions. So
I see.
This was just for visual reasons to provide, a visualization of a cube, and the people understand what we mean by a data cube. That's why I just had 3 dimensions there.
I see. Okay, got it. Thank you.
Any more questions? Actually, have you come across a case where for some observations you simply have no value on some of the dimensions? Like the value is maybe missing or something like that for that dimension. And then, as far as I know, people turn to various kinds of solutions to this problem. Have you come across something like that?
Actually, yes, you are right. We have identified many missing values, and not only the dimension values that were missing, but also the measures, or multiple measures or missing measures. Yes, this is a problem, but this is, I would say, a problem of the quality of the data, and if some values are missing. But the thing here is that we wanted to address some modeling challenges, let's say, and see if we have different approaches that can be followed in order to model a specific scenario. Which of them should we select and why? Which is the best approach in order to, let's say, address a specific challenge in the modeling of the cube.
Okay, thanks. Any other questions? Yeah.
Have you considered using STATO, the statistics ontology? And I noticed that for units you use something else, but there's a UO, units ontology.
No.
No, okay. Would you consider using, like, would you map to Stato and UO and other ontologies for interoperability in the future?
For sure, yeah.
Okay.
Okay, any more questions? If not, then let's thank our speaker again. And this concludes this session.